Okay, so in this video, I'm going to work through the practice test 2 to help you get ready for the final. And I'm going to kind of just do it as though I was a student, and I'm going to sort of like be fumbling around a little bit, finding the data that I would hope that you would know how to find quickly during a test. So really, I would just like you to think about getting organized and making sure you have all of your resources at hand and knowing where you can find the information that you need. So this question is all about the shape of the tetrachloroiodide anion. So I know that in order to determine the shape of a molecule or a polyatomic ion, I need a Lewis diagram. And it's as quick as, you know, the simplest way of doing this is really just to draw it out rather than look it up. So let's count up valence electrons, remembering that this is an anion and not forgetting to add the extra electrons needed for the charge. So iodine's in group 7, gives me 7 valence electrons, and then I've got 4 chlorines, they're also in group 7, gives me another 28 electrons, and then I get 1 for the charge. So 4 times 7 is 28, plus 1 is 29, plus another 7 gives me 36 electrons in total. Now iodine and chlorine are both in the same group, but iodine is lower down, so therefore it's going to be the central atom, and the chlorines will be my outer atoms. I'm going to put it in parentheses before I get going and put the charge outside, just so I don't forget it. Okay, so to get to the basic structure, I've used 2, 4, 6, 8 electrons, so that means I've got 28 electrons remaining. And now I'm going to complete lone pairs on my outer atoms by putting 3 lone pairs on each of the chlorines. So 3 times 6 is going to be 24 electrons used up in total. So I've got to take away 24. And so what that means is that I'm going to have 2 lone pairs on my iodine, and it's going to have an expanded octet. And that's okay because iodine is from, it's further on than period 3, so we're good there. Alright, so now I've got to read really careful whenever they're asking about the shape. Do they mean the electron group geometry, which they're normally pretty clear about, and that would be the arrangement of all 6 things that are around the iodine, or do they want the shape? Now the shape and the electron group geometry are the same when you don't have any lone pairs, but they're different when you have lone pairs. And it's pretty clear here. It says what word or 2-word phrase describes the shape of the ICl4 minus anion. So what I'm going to do, go to my book. Here we go. And in chapter 7, right at the end there where it says molecular shape and polarity, here's my VSEPR table. And in my ICl4 minus anion, I've got 2 lone pairs, and a total of 6 electron regions. So that gives me the square planar shape with a 90-degree bond angle between my groups, right? 90 degrees and a square planar shape. So this answer in here is going to just be square planar. And then we go, what is the angle between the iodine chlorine bonds? Well, it was 90 degrees, and they give a little bit of a warning. It says if there's more than one angle, pick the smallest, and that would be if you had your trigonal bipyramidal where you've got 90 and 120, right? Okay, next question's all about a Born-Haber cycle. Born-Haber cycle is about the formation of ionic compounds from a metal and a non-metal in their standard state. So you need to know the terms in order to kind of be able to understand how this happens. So what we've got is the formation of 1 mole of an ionic compound from its elements in their standard states, in their normal form, their most common form at room temperature and 1 atmosphere. And that's what's happening in this single step here. This in here is what we call the heat of formation, right, for this ionic compound. But you can consider that occurring in 1 step, or you can consider it occurring in a series of 5 steps. The first step, we go from solid metal to gaseous metal. That's called sublimation. In the second step, we're going to break the covalent bond between our non-metal atoms and go from being a diatomic molecule to being individual atoms, and that's generally referred to as the bond energy. In our third step, what we're going to do is we're going to rip off 2 electrons from our gas phase metal atom, and that's called ionization. And in particular, we're going to add together ionization energy 1 and ionization energy 2, but I'm just going to call that the ionization energy. In our fourth step, what we're going to do is we're going to add a couple of electrons to our gas phase non-metal atom, and we're going to form the dianion. That's called the Electron Affinity. And then finally, our cation and anion in the gas phase are going to combine, going to release a whole bunch of energy, and they're going to form the solid ionic compound. And the enthalpy change associated with that is the negative of the lattice enthalpy. All right, so because the lattice enthalpy is always a positive number, and this step always releases energy. So the first question says, what is the lattice enthalpy? So how are we going to figure this out? Well, we're going to go from 550 all the way down to negative 150. So 550 to 0 is going to be 550, and then we've got to keep going another 150 down. So that's going to be 700, isn't it? 700 kilojoules per mole. So that was pretty easy. You just had to know the term, what was meant by the lattice enthalpy, and then read the scale correctly. And then it says, what is the enthalpy of formation? Again, this is pretty easy. You just have to know which of these steps corresponds to the enthalpy of formation. And in this case, we're going to go from 0 all the way down to minus 150. So that makes it easy. Notice that we don't, by default, make it a positive number. We just read it off the scale exactly what it is, because it's the enthalpy from going from there to there. Could be positive, could be negative. Normally it's negative for ionic compounds. And then this last one is always a little bit of kind of tricky, right? It's always a little bit tricky. It says, suppose both the ionization enthalpy of M and the heat of sublimation of M were bigger. Would Mx be more stable or less? So what we've got to think about is, if I made the ionization energy and the sublimation bigger, basically everything would get on this side here would get like bumped up, right? Everything over here would get bumped up. So this top line here would be higher up, all right? Then the electron affinity would be the same, but that would lead to a bigger difference between the end of the electron affinity and the formation of the ionic compound. So the lattice enthalpy would be bigger, right? So it would be more stable, because the lattice enthalpy is a measure of how stable your ionic compound is. Now, there is another way of looking at this, right? And that's this. We know that the heat of formation is equal to the sublimation energy plus the bond energy, plus the ionization energy, plus the electron affinity, and then plus the negative of the lattice energy. All right? We know that, according to Hess's law, whether you go around those 5 steps or whether you go in one step, they all should add up to the same energy. So if I bring the lattice enthalpy over, and then I also bring over the enthalpy of formation, there we go. I should label that as lattice. Then I can convince myself of this even more so, right? And so what I'm going to do is I'm going to make the ionization energy and the sublimation energy bigger, and you can see that obviously that is going to make the lattice enthalpy bigger. Alright, so however you do it, whether you do algebra and you just use this little formula and think about what's going to happen, which is kind of the bulletproof way of doing it, or whether you just use the diagram and kind of reason it through, it doesn't really matter, but you should be able to get the first two parts correct without much struggle, and then a little bit of thought on the third part. Alright, answer the questions in the table below about the shape of the bromite ion. Okay, so same thing, we're going to add up electrons, right? So bromine's in group 7, then we've got 2 oxygens there in group 6, and then we have to add in 1 electron for the negative charge. So 2 times 6 is 12, plus 1 electron is 13, plus 7, 20 electrons. Okay, so what is going to be the central atom? What is going to be the outer atom? So it's a little kind of like confusing here, but we've only got one of the bromine, so I'm going to put that in the middle. Now, halogens don't normally go in the middle except for when they're combined with oxygen. And there's a little kind of bit of confusion here as to oxygen has the lower group number, and bromines normally, atoms from group 7 normally go in on the outer positions. So why is oxygen going in the outer position? Well, I think one way of looking at this is that the larger atom always goes in the middle. So, but in general, if it's a halogen with oxygen, the halogen goes in the middle. So the general layout's going to be like that, single minus charge. And then we used 2 4 electrons just to get the general structure. That leaves 16 electrons remaining. So now we're going to complete lone pairs on our oxygens. There we go. And so that uses up 2 lots of 6 or 12 electrons. And then that leaves 4 electrons remaining that are going to go on the bromine. All right. So this question is a little bit different. It says how many electron groups are around the central bromine atom, and then it gives you a bit of a prompt, right? It says that an electron group means 1 lone pair, 1 single bond, or 1 double bond. And what I can see here is around the central bromine, I've got 1, 2, 3, 4, right? Because an electron group is a lone pair or a bond of any type. So I've got 4 electron groups. And then it says, what phrase best describes the arrangement of these electron groups? So they're not asking for the molecular shape. They're asking for the arrangement of the electron groups. So when I go to my table, I'm looking in this first column. And so 4 electron groups is called tetrahedral. Okay, tetrahedral. So I'm going to pick tetrahedral. It is not bent. Bent is the molecular shape, or in this case, the shape of the anion. All right. So let's have a look at this. Perchlorate anion, ClO4-. So again, it's one of these little weird ones where even though chlorine's in the higher group, we're going to put it as the central atom because halogens with oxygen always go in the middle. So here we go. Cl is in group 7, and then we've got 4 oxygens there in group 6, and then we've got 1 for the negative charge. So 4 times 6 is 24, plus 1 is 25, plus 7 gives me 32 electrons. So chlorine in the middle, oxygen's on the outside. Note I'm not worrying about whether I need double bonds or triple bonds to get great formal charges, because I'm only interested in the number of electron groups here. So 2, 4, 6, 8 electrons just to get the general structure, leaves 24 electrons remaining. Complete my octets on my outer atoms. And there we go. All right, so I used up 4 lots of 6, so minus 24, so no lone pairs on my central chlorine. All right, so we're good at this point. So it says how many electron groups are around the central chlorine atom? There is 1, 2, 3, 4. Okay, And then it says, what phrase best describes the arrangement of these electron groups? Well, 4 electron groups is always tetrahedral. Okay. All right, so I'm just going to point something out to you at this point, and it's pretty simple. It's in many cases, Wolfram alpha, if I can, let's just do it this way, we'll be able to draw a Lewis structure for you. So let's see if it can do it in this case. There you go. And it put the double bonds in, but as you can see, it doesn't make any difference to the number of electron groups. So in many cases, you can get the Lewis structure. Now, I'm not certain how well it does with if you just put the formula in. But that's definitely something that you can quickly check a Lewis structure with. Yeah, so it's kind of having, you might need to know the name, you know. There you go. So it did okay with just the formula as well. So Wolfram alpha can be a good double check. All right. And also if you're speeding up. If you need to speed up because you're going slow. Okay, what is the angle between the carbon-oxygen bonds in the carbonate ion? So again, we're going to have to draw a Lewis structure. It's a little more clear cut here. Carbon and oxygen. Carbon's in group 4, oxygen's in group 6A, so we know that carbon's going to go in the middle. So counting up electrons, 4 for the carbon, and 3 times 6 for the oxygens, and then don't forget the 2. So that's going to give me 3 times 6 is 18, plus 2 is 20, plus 24 electrons. So we go, and as I said, carbon goes in the middle with the oxygens on the outside. Don't forget to write in the charge. So to get the basic structure, we've used up 6 electrons, and that leaves 18 remaining. And now we're going to complete our lone pairs. And that uses up all 18 electrons. And we can see that we're going to need 1 double bond to complete the octet on the central carbon. And of course, there would be the 3 resonance structures here. All right, but that's not so important. All we have to recognize is what's going on around the central atom here. We've got a total of 3 electron groups, and none of them are lone pairs. So I'm just going to go to my VSEPR table and look that up. 3 electron groups with 0 lone pairs is called trigonal planar. So in this case, the electron region geometry and the shape of the anion are the same. Okay, so it's just called trigonal planar. Make sure you get the spelling right. Here we go. What is the angle though? 120 degrees, 120 degrees, 120 degrees, right? Just from our table. 120 degrees. There we go. Now, all of those 3 bonds will be identical because there's actually 3 resonance structures, so it's going to end up being like a 1 1/3 bond, isn't it? And they all would be identical. You wouldn't get like one pushing harder than the other. All right, MO diagrams. You just got to read the instructions carefully. It says draw the molecular orbital electron diagram for the O2 minus molecular ion. So the first thing you want to do is count up the number of electrons that you're going to have. So 2 times 6 plus 1. So 12 plus 1, 13 electrons. So whatever diagram we use, we're going to have to put in 13 electrons in total. And then it says, be sure your diagram contains all the electrons in the ion, including any core electrons. So a single oxygen atom, 1s2, 2s2, 2p4. All right, that's the electron configuration. So we have to combine for every oxygen atom, a 1s, a 2s, and a set of 2p orbitals, okay? Now, your key here is to go to your book and to go to chapter 8 in your book, and you might want to like, make a note of this. Here it says molecular orbital theory, go there, and then you'll find that right near the end is a table where all of these molecular orbital diagrams are given to you. And sure enough, there's the one for O2. There's the order of the orbitals. And then here are the labels for them. Okay, so, I'm just going to grab that one and bring it over. I will point out a little something about this diagram, is it doesn't start, if you see here, with the core electrons. It starts with the valence electrons, the 2s, right? So we're going to have to add in, a little bit extra to get this correct. So we need to think about how the 1s combine on the two atoms. So when 1s orbitals combine, they're going to form a sigma 1s star and a sigma 1s bonding, aren't they? All right, so it's not too hard to add those two extra MOs in. All right, so this is going to go like this. It's going to go sigma 1s, sigma 1s star, that's the core, and then now I'm just going to copy the rest over. 1, 2, 3, right? Sigma 2s, sigma 2s antibonding, and then we've got sigma 2p, and then we've got pi 2p, pi star, 2p, and sigma star 2p. So there we go, and then all we have to do now is put in our 13 electrons according to Hund's rule and the Pauli exclusion principle, right? Which is basically don't double up in orbitals of the same energy until you have one in every orbital, and always put electrons in with opposing spins to the same orbital. So there's 6, 8, 9, 10, 11, and now we've got 2 of the same energy, 12, 13. All right, so all I have to do to solve this question was I just had to pay attention that it asked for not just the valence electrons, but the core electrons. I counted up the correct number of electrons, made sure that I was going to add that number of electrons at the end, and then I drew out the orbitals and labeled them correctly. All right, and how I did that was I just copied over the valence electrons from the diagram that was given in the book, and then I added in the core electrons, and I knew that two 1s always interact to give a sigma 1s and a sigma 1s star. So that was relatively easy, and then I just put everything in, making sure that I didn't violate the Pauli exclusion principle or Hund's law. So that's it, really. So we got that taken care of. 13 electrons. Looks like it's paramagnetic with one unpaired electron there. Okay, so this question is asking you to tag all sp3 hybridized carbon atoms in the molecule. So in order to figure out hybridization, you need to look at the number of electron groups around an atom. So it's pretty simple. If you've got 2 electron groups, it is sp hybridized. 3 electron groups, you got sp2 hybridization. 4 electron groups, sp3. 5 electron groups, sp3d. And 6 electron groups, sp3d2. So as long as you keep that in mind, you're good. So let's just have a look at that guy there. Remember that an electron group is a bond of any type or a lone pair. So that one there, it has 1, 2, 3 electron groups around it, so it's sp2 hybridized. So we won't be tagging him. And then the next one here, the lower one, that has 1, 2, 3, 4 electron groups around it. So 4 electron groups is sp3 hybridization. So this guy is the one that we're interested in. So it's that lower one there that we'd be tagging, this one here. All right, so that is sp3 hybridized. Pretty straightforward. It's just a matter of counting up the number of electron groups and then, assigning the correct hybridization. Okay, let's have a look at this one. It says, answer the questions below about the highlighted atom in this Lewis structure. So it's that carbon there, the red one, and it looks like it's got 4 electron groups around it, 4 electron groups. So that means a couple of things. It means it's got a tetrahedral arrangement of electron groups around it with a bond angle of 109 degrees. And it also means that it is sp3 hybridized. So let's see if that's what they're going to ask. It says, how many sigma bonds does the highlighted atom participate? Well, it's got nothing to do with what I just mentioned. Should have read ahead, right? Sigma bonds, remember that a sigma bond is formed by the end-on overlap of orbitals, not the side-on overlap, and a single bond is 1 sigma bond. A double bond is 1 sigma and 1 pi, and a triple 1 sigma and 2 pi. So in this case, we've got 4 single bonds, so therefore the highlighted atom is participating in 4 sigma bonds. How many pi bonds does the highlighted atom participate in? Well, it doesn't have any doubles or triples, so that would be 0. And then it says, what is the orbital hybridization of the highlighted atom? Well, we actually already answered that. 4 electron groups, it's sp3. Now, you can always add up the number of orbitals that are being hybridized, 1s with 3 p's, and that gives me 4, and that should always equal to your number of electron groups. So we know that that is correct. So this is sp3 because we've got 4 electron groups around that central carbon atom highlighted in red there. All right, on with the next one. What is the hybridization of the central atom in the iodine pentafluoride molecule? So the first thing that I'm going to notice here is that this is an iodine atom with 5 fluorines attached. So the Lewis structure is really either going to look like this, where there's no lone pairs on the iodine, or there's going to be lone pairs on the iodine. We'll have to figure that out in a moment. So there's only 2 possibilities for the hybridization. Either there is 1, 2, 3, 4, 5 electron groups, and the hybridization is sp3d, or there are 6 electron groups, and the hybridization is sp3d2. But we're going to need to get the Lewis diagram to decide that. So what have we got here? 7 valence electrons for the iodine, and then 5 times 7 for the fluorine. So 5 times 7 is 35, plus another 7 is 42 electrons. So now we've got iodine in the middle with the 5 fluorines attached. So to make those 5 single bonds is going to use up a total of 10 electrons. So I've got 32 electrons remaining to finish everything off. So then I'm going to put 6 on each of the 5 fluorines. There we go. All right. So that's going to use up 30 electrons, isn't it? 6 times 5, and that leaves 2 left over. So the 2 have to go on the iodine. So we know that this iodine, when I count up the electron groups around the center there, 1, 2, 3, 4, 5, 6 electron groups. So therefore, it's got to be sp3d2, right? sp3d2. Because it's got to add up to 6. So 1 plus 3 is 4, plus another 2 gives me 6. All right, so if I wanted to, I can go into there, IF5, Maybe it'll do it for me. And it did it for me. There we go. So we got it all. All right. So we can kind of, double check that just to make sure that we got it correct. Sometimes it works, sometimes it doesn't. All right. Looks good though. Well worth doing the double check. Okay. So if I were thinking about this, so we've got hybrid atomic orbitals in here. Let's have a look. There's a nice little table in here that could be helpful to consult if you ever get kind of confused. All right, so keep that in mind. So all we're looking at is the regions of electron density, and then that corresponds to the hybridization of our atom. Okay, so it's a pretty simple idea. So if you've got a good grip on VSEPR theory, it's not too hard to get the hybridization worked out. All right, on to question 10. It's going pretty well. Looks like we're doing another molecular orbital diagram for a molecular ion. And it says draw the molecular orbital electron diagram for B2 plus molecular ion. Be sure your diagram includes all of the electrons of the ion, including any core electrons. So the first thing I'm going to do is count up my electrons. So periodic table goes hydrogen, helium, lithium, beryllium, boron, right? So boron has 1, 2, 3, 4, 5 electrons. So we've got 5 electrons in total. We've got 2 borons, but then we took 1 away. So that means that we've got a total here of 9 electrons, all right? So that's pretty straightforward. And then what's the electron configuration? 1s2, 2s2, 2p, 1. 5 electrons, right? So the core electrons, obviously, they're going to be those guys. We're probably going to have to add those in. Let's go to our, so we know that we're going to be beginning with sigma 1s, sigma 1s star, aren't we? All right? Okay. So if we go to chapter 8, and I didn't have, oh, there it is. I got a tab there with it. Here it is, this diagram here. Copy my image over. There we go. Ooh, move. Ooh. Want just that guy to move. Oh dear. It's not liking how I'm laying things out, is it? I want to overlay you without you getting all antsy about it. There we go. All right. So what we can see is we've got to be a little mindful. Remember that the order of the pi 2p and the sigma 2p flips halfway across the p block. So it's going to be a little different from what we had for oxygen. So it's going to go sigma 2s star. Should label that correctly. And then we go into our pi 2p comes next. And then our sigma 2p. So you just got to be aware of that the first 3 get pi first. So sigma 2s star, pi 2p, sigma 2p, and then we got the pi anti-bonding. Now I only have to put 9 electrons in, so it looks like I've got enough orbitals here. So 1, 2, 3, 4, 5, 6, 7, 8, and then we go 9. So we see, you being mindful that you don't have to draw the whole thing out because we're only going to put in 9 electrons. There's not really much more that I would check here. That looks good to me. Okay, so in this question, I have to decide what intermolecular forces act between molecules of each compound. So the first thing, and there's 3 possibilities. There are dispersion, dipole, hydrogen bonding. So before I even get going, dispersion are always present between any particles. So I'm just going to put those in. Now, the requirement for dipole is that your molecule has to be polar. Okay, so polar molecules have an asymmetric distribution of atoms around of electron density around the central atom, we should say. So if I was going to do hypobromous acid, the Lewis diagram is going to be something like that, right? Okay, so it's going to be something like that. We could look it up, but you can see there's no way of arranging 3 different atoms so that it wasn't polar. It's impossible, right? You're always going to end up, so that's going to definitely be polar. Now carbon monoxide is a Lewis diagram that looks like that, and again that's definitely going to be polar, right? Now this guy, I should point out that it's probably polar like that. H2 is 2 identical atoms. 2 identical atoms bound together are neither polar. And then finally we've got fluoromethane. So we've got carbon with 3 hydrogens on it, and then we've got a fluorine there, and my goodness, you can see immediately that that's, oh, wrong way, that is most definitely going to be polar. All right, so that will have a dipole. Now, the requirement for hydrogen bonding is a little more complex. The requirement for hydrogen bonding is that your atom has a lone pair, and it also has an atom of hydrogen attached to either oxygen, nitrogen, or fluorine. So in the first case, and you can look up the Lewis structure if you want to, you'll see that we have both requirements. We've got the lone pair, and then we've got hydrogen, which is on oxygen. So this guy can hydrogen bond. Now, carbon monoxide, it's got the lone pair, but it doesn't have the hydrogen, so it doesn't meet the requirement. All right. Now, carbon monoxide could hydrogen bond through its lone pair to a different molecule. It just can't hydrogen bond to itself. All right. And then hydrogen, H2, no lone pairs. So, and hydrogen is not attached to oxygen, nitrogen, or fluorine, so that can't hydrogen bond. And then finally, we've got fluoromethane. It's got the lone pair requirement, but it doesn't have the hydrogen attached to oxygen, nitrogen, or fluorine, so it doesn't meet the requirement. So there's only one here that can hydrogen bond, and that is hypobromous acid. I also just wanted to quickly point out that if you go over to Wolfram Alpha and you put in the formulas of those compounds, you can get those Lewis structures pretty quickly as well, and that can be really helpful. So just to double check everything and make sure that your reasoning is sound. So just keep that in mind. Okay, let's move on to the next one. It says, what kind of intermolecular forces act between a hydrogen chloride molecule? So hydrogen chloride has that Lewis structure. Okay, so it is polar, but it has lone pairs, but it doesn't have hydrogen attached to oxygen, nitrogen, or fluorine. So it could potentially hydrogen bond to another molecule. And it says, and a dichloroethylene molecule. So this is interesting. We've got CH2CCl2. So the molecule is going to look like that. Okay, so it's clearly kind of polar, isn't it? All right. Yeah, it's clearly polar. It's like all of the electrons are getting sucked to the chlorine end of the molecule. So it's going to be kind of polar that way. It has lone pairs as well as being polar, but it doesn't have anything that can, any hydrogens that could hydrogen bond. So what kind of intermolecular forces? Well, there are always dispersion. These guys can't hydrogen bond with each other because they don't have hydrogen on oxygen, nitrogen, or fluorine, but they can interact via dipole-dipole because they are both polar. So this is going to be dispersion and dipole-dipole, or you can just put dipole is what Alex prefers. So let's see what happens if we put this into Wolfram alpha. Could we get a Lewis structure for that molecule? So it's CH2, CCl2. Let's see what it would draw for us. It says data not available, right? So sometimes it doesn't work, and you can see that there. So we were kind of on our own with figuring that one out. All right. This is an interesting one. It says 2 beakers are filled with different liquids. A steel ball is dropped simultaneously into each liquid. Drag the slider to see what happens. The stopwatch shows the time since the balls were dropped, and I moved the timer along a little bit. But what you see is that you have these 2 liquids, and according to the notes, they both have the same density. And in one of them, the ball drops a lot quicker than the other, right? So what is going to be different about these guys? Well, what it is the it's the viscosity, isn't it? Right? The viscosity is different. Yeah. Okay. So that's what's different about these. This one's like thick like honey. This one, this one is thick like honey. This one's runny like water. And so it's kind of an interesting phenomenon, right? If you had water, and then you've got like some oil, and you did the same experiment, you would expect that the ball would move quicker through the water than it would through the oil. And some people might be tempted to think that this means that water is more dense than oil, but nothing could be further from the truth. And we know that oil is less dense than water because oil floats on top of water. So the answer to this one is viscosity, how easily it flows out of the way and makes space for that ball to fall through there. Okay. Not quite certain what happened there. We got a repeat rather than question 14. Now we're just going to jump to question 15. Okay, I guess I don't help you out with question 14. So it says 231 grams of 2 different liquids are poured into beakers. Okay, so same mass. But what's obviously different is that they have different volumes. Yeah. So then it says, what's different about liquids A and B? Your answer should be the 1 or 2 word name of a physical property. So what's different about them? Density. Right? Liquid A is more dense than liquid B. All right? So that's it, right? Because the masses are the same, but the volumes are different, so therefore they have different densities. Okay, well, we did all but one question of that second practice test because we had 2 repeats of question 13. But anyway, I hope you found it helpful, and I'll post the third one soon.